over h bar. And now what comes out here is mq dot j squared minus v of qj. Okay, so this is all, how you do that's completely explained on a handout you'll get. So, and it's a good exercise just to work through, just to understand the handout and make sure you agree with this and see where it comes from. And what you should recognize, so we start with the Hamiltonian, which was, of course, kinetic plus potential energy. And, sorry, I missed out a factor of a half. And what we end up with is kinetic minus potential energy, and that's the Lagrangian. So this is just the Lagrangian of Q evaluated at position Qj with velocity Qj dot. So we're going from a Hamiltonian to a Lagrangian. So putting it all together then just to get the result. Remember, this was just one of the factors. We had n of these factors in here, but that's okay because we just got an overall constant thing out here, and then we get exponentials. And when you multiply together exponentials, of course, you just sum up the exponents. So qf e to the minus I over h bar, over h bar, h t qi. Okay, so to this order, well, in fact, so to be precise, it will be the limit as n goes to infinity or as delta t goes to 0. So we'll get n of these factors, so we'll have minus I m over 2 pi h bar delta t. So that's n to the power of n half, then we've got n of these factors. And then we get a factor of this. Well, this is the one at qj. We'll start all the way from q0 all the way up to qn minus 1. So we'll get it. And basically then what that's doing is just summing over that Lagrangian. So we exponential of I over h bar sum n equals 0 to n minus 1, if you work out how many factors there are, delta t times the Lagrangian of j equals 0 to capital N minus 1 of qj dot. And taking the limit now is actually trivial, which gives us our final result. Sorry. Missed out an important point, of course, that we have all these integrals, dq1, dq2, dq n minus 1, sitting in there. So basically you define these integrals along with this factor. So this whole thing here okay, so it's just an integral over all the intermediate positions, and you've got some normalization factor. So the point is we don't know quite how to define an integral over all paths, but it certainly has something to do with all possible intermediate positions, and this is just some normalization factor that comes along with that. So we just give it that symbol. So we haven't done anything here, we're just giving it a symbol. The interesting bit here is, of course, when we take small steps delta t, we've got this Lagrangian, which is a function here, and we're taking the value of the function times delta t and summing it all up. And that's just the definition of integration when we take delta t to 0. So that just becomes exponential of I over h bar integral dt of the Lagrangian. Okay, so that's nothing else than fundamental definition of integration. And then we get our final result, of course, is just what I said we would get at the start, is just that the integral of the Lagrangian, of course, is just the action. So this thing here is just the action, which depends on some chosen path, q of t. It contributes then, this is the amplitude, is the exponential of I over h bar times the action, and for a given path, and then you sum over all possible paths. So that's what the path integral is. So it's a good place to stop, because what we'll do next time then, so as I said, we could have independently just started from that, given some meaning to what this meant, and said that was the definition of a path integral. And we could have defined quantum mechanics that way. Then I could have gone back all the other way and shown you that it was equivalent to this, and it gave you equivalent to what you know in terms of wave functions and so on. But we've derived it from the wave functions, and we get this. So what we'll do in the next lecture then is actually see what advantages doing quantum mechanics this way gives us. So the first one is, how on earth do you pick out the classical path? Why does classical mechanics work, given that quantum mechanics is written in this form? What's so special about the classical path in this way? And this gives a very nice way of seeing how you go between quantum mechanics and classical mechanics. And then we'll see some examples. And again, the examples we'll do all involve Gaussian integration. So it's well worth looking at that intermediate step there that I missed out, along with this handout. Okay, so that's all for today. So I should say I'll be around all the time, so if people want to come and ask any questions, I'll be available.
Any questions now? Should encourage you guys to ask questions during the lecture. Don't be afraid to ask as many questions as you want. It's fine. We'll change the lectures to accommodate
yes.
time. So just a few announcements. One is that tea is downstairs now in room 216. That's one floor down and across the building. And for those of you who want to check email and stuff, we have computer facilities available. That's an SSH terminal and a browser. There's 18 machines available upstairs. The room will only be open during the tea times. So if you want to check your email upstairs, and now is the time to do it. Okay. Those of you who haven't registered yet, Catherine Benfield will be outside. Please do so. Collect your name tags and your folder.
Right.